This is active filter design. Lecture 4. Yesterday we saw that in order to get a squared magnitude response which kind of looks like this, where this is the approximation band, this is 0 to 1 or the pass band, it's 1 here and 1 by 1 plus epsilon square here, okay. And we find that mod h of j omega square can be written as 1 by 1 plus epsilon square Cn square. In this particular picture, the order of the filter is is 5, and how do you get that 5? You can count the number of peaks and valleys. So this is 1, 2, 3, 4. Okay. This is an example of a fifth order so-called equiripple approximation. Okay. And yesterday, after all that math, what we said was that Cn square of omega looks like this. This is 1, this is 1. Okay, we call this omega 1, omega 2, omega 3 and omega 4, and we concluded that Cn square of, actually we also know that it's an even function of omega, so it's a function of omega square. Cn square is of the form k square omega square times omega square minus omega 1 square the whole square times omega square minus omega 3 square the whole square. Okay. And then we exploited the following three facts. Omega 2. Cn square is k square omega square times omega square minus omega 2 square the whole square times omega square minus omega 4 square the whole square. We exploited the following three facts. One is that Cn square of omega square goes to 0 at omega 2, omega 4, and also minus omega 2 and minus omega 4. We also said that it's not simply enough if I find some polynomial which goes to 0 at 0, omega 2 and omega 4. In other words, an arbitrary choice of omega 2 and omega 4 will still satisfy, will make Cn square, the polynomial squared, go to 0 at those frequencies. Okay. But what can I conclude about, what is the problem with making an arbitrary choice of omega 2 and omega 4? It's not very likely that the peaks will be the same. Okay. Intuitively you can understand that by simply mentally perturbing omega 2 to the left a little bit, and immediately it's apparent that the left peak will go down while the right peak will go up. Okay. So it's not just simply enough if this is true. We also need Cn square of omega square minus 1 to go to 0 at omega 1, omega 3 and 1. Right? Now, this is where I would normally stop, right? But given the prowess of these mathematicians who did this about 120 years ago, right? They also realize that omega 1 and omega 3 are maxima and omega 2 and omega 4 are minima. Correct? And use this and finally end up with a differential equation relating Cn and omega. So this is all background material of what was done yesterday. So dCn by Cn square minus 1 is d omega by square root of omega square minus 1, and this implies that Cn of omega is the form, n d omega by square root of omega square minus 1. So Cn of omega is cosine hyperbolic of n cosine hyperbolic inverse of omega. Right? At first sight, this seems a little puzzling, given that we were after a polynomial. Correct? I mean, all along we've been assuming that Cn square of omega square is a polynomial, and suddenly cos hyperbolic and sine hyperbolic, cos hyperbolic and cos inverse hyperbolic and all this stuff starts coming up. Kind of, at first I'd be a little puzzled, given that, hey, this hardly looks like a polynomial, right? Okay, that is one issue. Is this a polynomial? And two, cos hyperbolic inverse, as we know it, is only defined for, cos hyperbolic, the function itself, if you assume a real argument, takes values which are always greater than 1, right? Which means that the inverse cos hyperbolic is not defined for in the range 0 to 1, which is our passband. Okay, but that we didn't worry too much about it, because the moment you start allowing complex arguments, then it becomes straightforward, as I'll show you. What about the range 0 less than omega less than 1? These are the two questions that one would ask right away. So let's address the second question first. Alright, and to do that, I just want to bring to your attention a couple of simple facts. Cos theta is e to the j theta plus e to the minus j theta by 2, right? And cos hyperbolic, or cos of j theta, is e to the minus theta plus e to the plus theta divided by 2, which is the same as cos hyperbolic of, okay. So in other words, and what is cos hyperbolic of theta? What is the minimum value? 1. So turning this upside down, if you want to find the inverse cosine of a number, right? The number is less than 1, it's the traditional inverse cosine. Okay. If the number is greater than 1, then we find the inverse hyperbolic cosine and then tag on a j2. So let's see. So we want to find, for example, we want to find a cosine inverse of omega where omega is greater than 1, let's say. Okay. So let's say cosine inverse of omega is y, which means cos y is omega. If omega is less than 1, y is nothing but, y is nothing but cos inverse omega as usual. If omega is greater than 1, then what do we say? Y must be, omega is greater than 1, then y must be of the form jy1, right? And cos of jy1 must be equal to omega, which is greater than 1. And what is cos of jy1? Is cos hyperbolic y1. This must be equal to omega, correct? Which means y1 is cos hyperbolic inverse of omega, which means y is j cos hyperbolic inverse. Does this make sense? Okay. Right. Similarly, if we want to find the cosine hyperbolic inverse of omega, if y is greater than 1, there is no problem. It's nothing but the usual cosine hyperbolic inverse. Now, if y happens to be less than 1, obviously there is no real omega that will satisfy this equation. Okay, so that basically means cos hyperbolic of y must be equal to omega. If omega is smaller than 1, then we assume y is jy1, and cos hyperbolic of jy1 is nothing but omega. What is cos hyperbolic of jy1? Right? I haven't discussed that, but yes. Okay. Cos hyperbolic of jy1 is nothing but e to the jy1 plus e to the minus jy1 by 2, which is nothing but cos y1. Correct? Which means cos y1 is omega, which means y1 is cos inverse omega, right? Which means y is j cos inverse. Does it make sense? Yeah, you can, right? But you will find that the real part will tend to, the other part will, you can expand. The question is, how did you know that, this number here is only imaginary? In reality, what you should do is substitute a plus jb and then expand cos hyperbolic as a sum of, cos a, cos hyperbolic a, cos hyperbolic jb plus blah blah blah, and equate real and imaginary parts on both sides, right? Since we already have been saying that cos hyperbolic of, cosine of an imaginary number gives you the cos hyperbolic of the imaginary part, I thought it's pretty straightforward without having to go through the extra. Do you understand the question? The question he raises, how did you know that in general should the argument be a complex number which we would like to find? Okay, yes, that's the correct line of thought. Okay, the only reason why I bypassed all that is because we seem to have understood that the moment you put an imaginary number for the argument in the cosine, it will become a hyperbolic cos which goes larger than 1. Okay, we will have opportunity to do the general thing in just a couple of minutes in another context. So, alright, so now that we have understood this, let's try and figure out what Cn must be in the range 0 to 1. So, Cn is cos of n cos hyperbolic of n cos hyperbolic inverse of omega. For omega less than 1, what is this guy? For omega less than 1, what is this? J cos inverse omega. Okay, and this is cos hyperbolic. Okay, now what is cos hyperbolic of j n cos inverse omega? It's simply cos of n cos inverse. Does it make sense? So, if you you want to keep everything real, then you say Cn of omega is cos of n cos inverse omega for the range 0 omega less than equal to 1, and becomes cos hyperbolic of n cos hyperbolic inverse of omega for 1 the rest. This is clear. Okay. And though all of us may not be very familiar with expanding multiples of an angle of a hyperbolic cosine, for the real cosine we are all very familiar, right? For example, C1 of omega is nothing but cos of cos inverse omega. What is that? Omega. What is C2 of omega? Is cos of 2 cos inverse omega, and which is, how will you find this? Can you expand this? Cos 2 theta is 2 cos square theta minus 1. Correct? So what is this C2 of omega? 2 omega square minus 1, and we see, lo and behold, this is indeed a polynomial. Okay? Cos 3 omega, C3 omega is what? Cos of 3 cos inverse omega, and what is cos 3 theta? 4 cos cube theta minus 3 cos theta. So what is C3 of omega? 4 omega cube minus, and so on and so on. Okay, so this solves both our problems. Now we have defined these polynomials. I mean, it turns out that they are indeed polynomials. Okay, in fact, if you remember the expansion for multiples of an angle in the hyperbolic cosine, you will end up with the same thing. Okay, so this is indeed, these are indeed polynomials, and they are defined over the entire range in this fashion, and these have a special name after the person who came up with this. These are called Chebyshev polynomials. A mathematician who worked on this for a long time. This is just the surface of what is called Chebyshev approximation. Okay, the full theory of Chebyshev approximation is actually exceedingly complicated. Definitely not suitable for a class such as this. And this is called the Chebyshev approximation. And quite logically, a filter with this characteristic is called the Chebyshev filter, also called what is called the equiripple approximation. Okay, why equiripple? The magnitude of the ripple kind of remain constant. Okay, there's also another name for this. I'll first give you the name and then explain why it's called this way. It's called the Minimax approximation. The intuition behind calling this the Minimax approximation is the following. As I mentioned to you several times, these values omega 1 right, the choice of omega 2 and omega 4 is indeed not arbitrary. Okay, now if I move omega 2 to the left or right, or omega 4 to the left or right, away from their values which were found from the Chebyshev approximation. Please note, we already know the polynomials now. So in principle, finding omega 1, omega 2, omega 3 and omega 4 is trivial, because we know the form of the polynomial. We'll find when the To find omega 2 and omega 4, we will like to set that polynomial to 0. To find omega 1 and omega 3, we set the polynomial to 1. Okay, so omega 1, omega 2, omega 3 and omega 4 are found very easily. We'll find them in a jiffy. But at this point, all that I want to point out is that these omega 1, the choice of omega 2 and omega 4 is not arbitrary. Right? These are some special smart ways of choosing omega 2 and omega 4. If I move the perturbed omega 2 and omega 4 away from their values given by the Chebyshev approximation, then what do you think will happen to the height of the left ripple? The two ripples, the height of this peak and this peak will no longer be equal. So we are trying to approximate 0 here, correct? So if the peaks are no longer equal, what can you say about the magnitude of the maximum peak? So it will be greater than 1, correct? So if I move omega 2 or omega 4 away from these optimal values, what happens is that the maximum deviation from 0 increases. So in other words, this particular choice of omega 2 and omega 4 is that which minimizes the maximum deviation from 0. You understand? Okay. So that is why this is called the special choice of omega 2 and omega 4 minimizes the maximum deviation or error. Okay, that's why this is called the Minimax approximation. Yes. To do our one, let us see what happens when n is even. So far we have chosen n to be odd. Okay, where n is even, it turns out that you proceed pretty much the same way. There's some minor differences in derivation, but finally you will get the same polynomial. Cn is cos of n cos inverse omega in the pass band, and cosine hyperbolic of n cosine hyperbolic inverse omega in the stop band. And at 0, let me take a particular example. N is say 4. Okay, so in the pass band it is cosine of 4 cosine inverse omega. What is it at 0? What? It is 1, whereas C3 of 0 is what? 0. So in other words, for an even order Chebyshev filter, how will it start? The even order Chebyshev filter will not start from filter transfer function. It will not start from 1, it will start from 1 by 1 plus epsilon square under root. So it will do this 1, 2, 3, 4, and this still remains. Is that clear? Whereas an odd order filter will do 1, 2, 3. Pardon my drawing. So this is 5, this is 4. Okay. By looking at the ripples, therefore, you should be able to figure out the order. Okay. The next thing that we need to do is find the frequency of. We'd like to find what frequencies these maxima and minima of transmission occur. maxima, what happens? Cosine of n cosine inverse of omega must be, for a maximum of transmission of the filter, what must this be? What must the polynomial be? Come on, people. If cosine of, if Cn is 1, what is the transmission? What is the transfer function of the filter? 1 by 1 plus epsilon square. Is that the minimum or the maximum? That's the minimum of transmission in the passband. Correct? So if you want the maximum of transmission in the passband, what should you do? Equate this to 0. Is this clear? Okay. Which means that n cosine inverse omega must be 2m plus 1 times pi by 2, where m is an integer, 0, 1, 2, blah blah blah, which basically means that omega is cosine of 2m plus 1 into pi by n, m is again 0, 1. For example, for n is 5 that we were looking at, the maximum of transmission are omega equal to cos of pi by 10, cos of 3 pi by 10, cos of 5 pi by 10, cos of 7 pi by 10, and cos of 9 pi by 10, 11 pi by 10 and pi by 10, and 11 pi by 10 and 9 pi by 10 are the same. Okay, cos of both of them are the same. So how come you're getting 1, 2, 3, 4, 5 maxima? Not only omega is positive, it's an even function, so there must be a maximum transmission in this thing also. And as we expect, there must be a, what is cos of 5 pi by 10? 0. Omega equal to 0 is definitely a maximum of transmission. That must come out. Correct? Now similarly, what are the minima of transmission? Omega is given by cosine of m 2m, what is this, m pi by okay, alright, and so m becomes 0, 1. So when you want the minimum of transmission, Cn must go to its maximum, right? And vice versa. Alright, so this is easy to compute. All that I am saying is, once you know n, you find that. Okay. Alright. What happens when actually it is m pi, isn't it? It is m pi only. Why 2 m pi? As epsilon increases, what happens to the passband ripple? As epsilon increases, what is the maximum of transmission? It is 1. Minimum of transmission 1 by square root of 1 plus epsilon square. So if epsilon increases, what will happen to the ripple? The magnitude of the ripple increases. Is that clear? Okay. So, okay. Now, if epsilon as epsilon goes up, ripple goes up. What can you say about the behavior at very high frequency? Is there more rejection or less rejection? Pardon? There is more rejection. Why? So Cn, for large omega goes as we saw yesterday, some k times omega to the parent. Correct? Okay. Now this k times omega to the parent remains the same because the same order is what we are concerned about. We are only trying to figure out what happens when epsilon increases. Correct? So high frequency rejection gain goes down, right? So in other words, in a picture, this is some ripple, okay? If I increase the ripple, this is a grossly exaggerated picture. What do you think will happen to the maxima and minima of transmission? What about the minima? Of course, but at the frequencies at which they occur, can you comment on that? They remain the same. Okay. So if I increase the ripple, this is what it will look like. Okay. Right? Okay. Any questions? Everything is clear? Okay. So this is actually pointing out something else, which is, can you look at these two pictures and tell me these two responses and try and guess something? So if you allow more ripple, you will have a sharper. Okay? You understand? So increased ripple. I mean, this is not. This is well. I've shown this here for a Chebyshev filter. It follows that. It turns out that this is a general rule. If you want to have very tight control over the pass band, then you will not have, you will not have a very sharp roll off. Okay, so now taking this one step further, what do you think? If you have a Butterworth and a Chebyshev filter, which do you think, both having the same 3 dB frequency, which do you think will have a sharper cutoff? Chebyshev will have a sharper cutoff because you are allowing for a lot of error in the pass band. Butterworth is attempting to make it flat. Okay, so it can't do a good transition band. Okay, so this is a general. The next thing to do is therefore to find we have found the expression for the squared magnitude. The next thing, is that what we are after, or we want something else? We found that mod h of j omega square is 1 by 1 plus epsilon square cn square of omega square. Right? Cn of omega, whatever, right? Cn of omega the whole square. Alright? So, okay, so what? We found Cn of omega. What now? We want to find h of s. How will we find h of s? How will we find it? We want to find the roots of the denominator. So, in other words, we want to find 1 plus Cn of s by j the whole square 0. Right? Now, this is a polynomial, we know that, of degree 2n. We want to find its roots, identify the roots in the left half s plane with d of s and and the right half plane as d of minus s we discussed before. So, what is this now? How will I find this? So, Cn of s by j is nothing but plus minus j by epsilon. minus 1 goes that side, that's j square, right? Which means that Cn of S by j must be plus minus j by epsilon. We want to find all complex numbers S that will satisfy this equation, which therefore mean that all those complex numbers will be poles of d of s and d of minus s. We only retain those poles in the left half S. Okay. Now, what is Cn of s? We can use one of our favorite stuff. We use cosine of n cosine inverse of omega, which is s by j, is plus minus j by epsilon. Okay. We have to find s. So we do it in two steps. We assume in general that this is a complex number u plus jv, where both u and v are real. Correct? Cosine of some number is something. Okay, we need to find that number. The right side looks complex, so it's reasonable to assume that, the general thing is to assume that the argument is also complex. Now, what is cosine of u plus jv? It's cos u cos jv minus sin u sin jv, and this must be equal to plus minus j by epsilon. Now, what is cos of jv? Hyperbolic cosine of v. What is sin of jv? Sin jv is e to the j into jv minus e to the minus j into jv divided by 2j, which is e to the minus v minus e to the v divided by 2j, which is minus e to the v minus e to the minus v by 2j. Minus 1 is nothing but j square. This is nothing, so therefore this is nothing but j sin hyperbolic. Correct? So this okay. Now look at that equation, this gap. The complex number on the left is the same as the complex number on the right, and u and v are real numbers. So what should you do? Equate the real and imaginary parts. Look at the real part. So cos u, cos hyperbolic v must be equal to 0. But what is cos hyperbolic v? The minimum value is 1, right? So that can't be 0, which means that cos u must be 0, which means that u must be of the form 2m plus 1 times pi by 2. Is this clear? Okay. And if cos u is 0, what is sin u? Plus or minus 1, right? So it basically means that minus j or plus minus j sin hyperbolic v is plus minus j by epsilon, which means that v is plus minus sin hyperbolic inverse of 1 by epsilon. Correct? So in other words, u plus jv is nothing but 2m plus 1 into pi by 2 plus minus sin hyperbolic inverse of 1 by epsilon. But u plus jv itself is nothing but n cos inverse s by j, which means I'll remove, so s by j is nothing but 2m plus 1 times pi by 2n plus minus, sorry, there should be j sin hyperbolic, right? Plus minus j to 1 by n sin hyperbolic inverse of 1 by epsilon. Cosine of this where what is the m stand for? M is an integer and what is n? N is the order of the field. Okay. Now for the last bit of fun, you just expand. This is now cos of whatever, you know, a plus b. This is nothing but cos of 2m plus 1 into pi by 2n, cos of 1 by n, cos of j by n sin hyperbolic inverse 1 by epsilon, which is cos hyperbolic of 1 by n sin hyperbolic inverse of 1 by epsilon, right, plus minus sin of 2m plus 1 pi by 2n, j sin hyperbolic of 1 by n sin hyperbolic inverse of 1 by epsilon. Which means the roots are plus minus sin 2m plus 1 to pi by 2n sin hyperbolic of 1 by n sin hyperbolic inverse of 1 by epsilon plus j cosine 2m plus 1 pi by 2n cosine hyperbolic of 1 by n sin hyperbolic inverse of 1 by. Okay, we'll continue in the next class.